we are done with the decision tree. The decision tree is over for us. Now we are at another algorithm called linear regression. Linear regression and classification. Now, what the linear regression and classification will do, you will get it so easily because previously we have talked a lot about how the algorithm works, how to minimize the outputs, and what sort of things we can do with the algorithm. So we are here, we are just supposed to, if you will just know the terms and you will get the understanding that what's happening behind the scene. So what is the linear regression? First thing is that the linear. First you will say no, right click linear. Linear means it is linear. First thing is there, it's a linear function. First is there. Regression says that we want the output which is not just divided into two terms, like yes, no, 1 2 3 4, not like that. Linear regression will be like the output could vary from one to another in any sense, like the half or price of the house. So it's not fixed, it's not just like either 1000 or below 1000. No, it can be 1000, 1 lakh, 10 lakhs, 20 lakhs, it can be anything. So that sort of problems are called regression, and I hope so you know this thing. Classification is when we are classifying a thing or the output in certain groups. So that's called the classification, that either this is yes or no, either this is 1 or 2, either this is 4 or 5 or 6 or 2 or 3 groups or whatever. Like it's easier to divide it in a group. So that sort of problems are called the classification problems. Now as soon as I talk about the linear classification and regression, so first thing that we should know, what's the formula for a line. So because we have to make a line that is like that is convenient for all the outputs, and that's the weights can be evenly distributed towards the, like we can get the what you can say, like we can get the minimum distance from every output that's available in the training set, and then from there we can use that same weights and everything to get the outputs that's never been seen by the algorithm. What I mean by that, if I say y is my output, then I'll say the linear formula is simple. That's the linear formula. Or if you see in mathematics, we could have seen mx plus c. You see, so I have changed these all things with the weights because we will change the weights. These are not constants. With every step of the problem, we are going to change the weights according to that. So that's why changed by changing the relative weights of one term or another. Here we will define w as well as a vector of w0 and w0. So if I put it in a formula way, in a linear regression way, I will just write this as w1x plus w0. So this denotes that this is what my expected output is, where we are using a hypothesis on x to get some output y. This you can just understand like this. We are using an hypothesis on x to get an output y, wherein we are using this formula to say that this everything that we have been using will like go according to this formula. Getting my point? This is the formula that has been used to prove my hypothesis on x to get my output y. If that makes sense to you. If not, you can just comment me and I'll make something more easier for you to understand. So now the task of finding, like we have to find HW that best fits this data. This is called linear regression. To fit a line to the data, all we have to do is find the value of the weights. If we find the value of the weights, we are done. And it's not that just we are finding the values, we have to minimize the loss. And the traditional way, like traditionally what we are doing is using the L2 weight. If you know, L2 is like the squared error. I had told in the previous videos what L1, L2, L01 is. So L2 was the square. So now we have to reduce this squared error. So how we can give that? Let's leave this thing. It will be, I will change this as well. Okay, right here, something called HW of x is equal to W1x plus W0. Okay, so I have this. Now I have to find the loss function, that's the HW, which can be given by j is equal to 1 to n. Okay, I have to find the L2 loss on y1 and HW of xj. Okay, so this thing is what we have to do. We have to minimize this, and here firstly I have to find the L2 loss. Okay, just be with me. Okay, don't lose the hope. We will go there. So now what it is, j is equal to 1 to n. What is L2 loss? It's the squared loss, y2 minus hw x of j, and this is what it is. Simple. If you see, this is what I have done. This is not j, this is j. Yeah, so this is really simple. If you see, now what this basically is, why I'm writing 1 and 2 over here, this is j. Okay, so this will be yj minus this formula. If you see, x in the place, x is like the for the 1, for n numbers we will change 1 2 3 4. So for j, what we will do is w1 x j plus w0 the whole square. Now what we will do, what we have to do, we have to find the weight, and that we can give, w can be given, this is like the minimum weight we can get is argmin of w on loss function h of w. So this is what my goal is, to like the minimize. Now the sum is this one, that I have already written. This is what we have to find. To minimize this, we will, what we will do is, firstly I will differentiate this with respect to w1, then w0. Then we will get two different and unique solutions. This different and unique solutions is our problem solution. Now how we will do that? So first what we will do, I will just remove this because now no space. If you want to write it, just you have the pause button with you, and what, just there is nothing, just and anything. So now what is there, w, firstly we will do it with w0, differentiating it, j is equal to 1 to n yj minus w1 xj, sorry, w1 xj plus w0 the whole square is equal to 0. Now as soon as I differentiate it and equate it with 0, I'll get the minimum w's, like minimum losses. This was my loss function which I have got, and now this is what we are trying to minimize it. Now firstly with the w0 and then w1, this same. So you can just write it the same thing here, this same is equal to 0. firstly with the W0, then W1. This is what we are supposed to do. Now these will have the unique solutions, and this we will get as W1 is equal to n. Just solve just a simple differentiation, there is nothing lot to do with that. Xj yj minus xj yj whole divided by n xj square plus sigma xj the whole square. Now we will have a W naught as well. W naught will be given by, this is simply yj minus W1 xj this whole divided by n. So this is what we have got, and this is what we are supposed to find in always. And now there are like one thing which we can say, like there are many forms of learning involved, like to adjust the weights. So if we will do like that, we'll always have a mental picture of the what's going on in the like weight space. The possible space defines all the possible settings of the weights. So if we know these things, so we will actually, like every time we are solving it, we are just getting the pictures like what's happening and how it's happening. So it's like good for you to know this. If you don't know this, then you have the libraries, but yeah, if you know this, then you will like use the libraries very well, because you know how the things are working and how you can, like what sort of things that can be needs to be changed with that. Now in all, it's like always seen as in the linear function. Whenever it's a linear function and we are trying to solve it, and for every linear function we get a convex solution if it's been solved, if it's been solved with the L2 error. So we can it's like in almost every cases that you will not have a always not have a minimum solutions. You see, so finding a local minimum in a linear solution is always like very impossible. Like I will not say impossible, but it's always like you can never find the local minimum. It's always the convex. So that's why this is what like the my video on this linear regression and classification is. This is basically just the formula. We'll again go with the codings now, because now we are at a position to codes as well. So that's it for today. Thank you. Hope you enjoy it.